Right, we're going to practice factoring. The goal here is that if we're asked to factor, or if we recognize that factoring is necessary to solve a problem, that we understand the different types of factoring techniques and what is necessary in order to get our problem solved. So what I did is I started with a priority list. In any time that we know we want to factor, we should go down the list of options here and just check to see if we can perform any of these techniques, and that should help guide us into what we can and can't do and what we should try, starting with the easiest methods first and working down to harder methods. Now, this isn't a complete list, but it will definitely get you started if you are having trouble factoring even from the beginning. So no matter what kind of expression we're dealing with, we're always going to try to factor out a greatest common factor, if possible, right? But we should always check. After we check for a greatest common factor, we're going to determine what we can do based on how many terms we have. So if we look at the expression and we see that there's two terms, these three formulas should come to mind, and we should consider if we can use either of these formulas in the problem that we're dealing with. And if not, then we would move to other techniques. So the first one is what we would call the difference of two squares, and then we have actually the sum and difference of two cubes. Now, keep in mind that there is no sum of two squares formula. So if we're being asked to factor something that's a two-termed expression, they're both perfect squares, each term is a perfect square, but they're being added together, it just doesn't factor. There is no formula for it because it doesn't work. If there's three terms in our expression, then we're going to do, there's a few different trinomial factoring methods. AC method is a pretty generic one that a lot of people are familiar with. There's a lot of other ones too, so when we get there, we'll talk about how that'll work. If there's four terms, we're going to look to do what's called grouping. And if any of these break down, then there's more difficult, time-consuming methods that would work, but we're not going to go that far today. All right, so let's practice some. So the first thing that we're going to do is recognize how many terms we have in the expression. That way, when we go through our steps, we can make sure that we're following them correctly. So keep in mind that a term, as I'll kind of keep mentioning it, the best way you can think about a term is it's a group of multiples. Now, that's not the technical definition, but it's a good way to think about what we see versus what we're looking at in terms of what we want to factor. So in this case, this expression has two terms. Right, there's the two of them. And we can see the groups of multiples by thinking about what it is that's being multiplied together. And then the first step that we're going to look to do is factor out a greatest common factor. So in this case, this first term, we can think of it as 3 times x, so we can see each multiple in this term. Then we're subtracting multiples of 12, but since we're looking for common multiples between the two terms, we could say that 12 can be broken down into 3 times 4. And if we do that, then we can actually see, as far as factoring out a common multiple from both terms, we could see that each of these two terms has a multiple of 3 in common. So what we're going to do is we're going to sort of keep the two terms grouped together here. So I'm going to keep underlining the two terms so we can kind of see what's left when we factor things out. Now we recognize that there was a 3 that each of these terms in this expression have in common, so I'm going to actually pull the 3 out. inside the parentheses, and anything outside the parentheses when we factor is a multiple. So by breaking down the terms into its multiples here, we can see that if we factor out a 3 from both of them, we can actually see what's left in each term. In this first term, there's an x. We're still subtracting the two terms. And if we factor out the 3, we're left with the 4. Now, the great thing about factoring is if we're trying to make sure that we did it correctly, we could always undo what we factored, which is basically, in this case, distributing the 3 back in. So if we were to distribute the 3 back to each term as multiplication, we should get what we started with. 3 times x is 3x, and 3 times negative 4 is negative 12, and this is exactly what we started with. So we know that in factoring, if we pull out a 3 and we're left with an x minus 4, that is as much as we can do, because we can't pull anything else out of the two terms, and since we'd redistribute it, we know that we factored it correctly. So this would be what we would call the factorization of the original expression. Okay, let's try another one. So same idea, we want to factor it. We're just going to recognize how many terms we have, right, before we move on. So I know that there's 2 terms. If you're not really familiar with what we're trying to see as far as terms go, basically what we can do is break down everything that's being multiplied and kind of put things together. So in this first group of values, 4x squared, we can recognize that there's a 4 being multiplied by an x squared value, and then we're going to add an 8, and the 8 and the x are going together by multiplication. So we can actually see the 2 groups of multiples here that justify our 2 terms. So if kind of laying out spaces between things that are being multiplied to kind of make all the values look a little simpler and how they're being put together so we can focus on the operations. If that helps you recognize what is considered a term, then by all means I would suggest to do that. Once we see these 2, though, step 1 is going to be to factor out a common factor if there is any. So what we're going to do is we're going to break this down again. So we know that 4 can be written as 2 times 2. And we know that x squared, the square just means how many of this base value we have multiplied together. So that means that there's 2 x's being multiplied together. This is all the pieces of this first term here, right? Now we know we're going to add the multiples over here. Now if we break down 8 as far as possible, we could say that 8 is 2 times 4, but we know that 4 is 2 times 2. So really 2 times 2 times 2, 3 of them all together would multiply together to make 8. So if you wanted to break them down to its prime multiples, then that would work. But once we see all of these pieces laid out, the idea of a greatest common factor is to pull as many of the multiples that each term have in common out. So in this case, we can see that there is a 2 that both of these terms have in common, so we can pull that out. Now there's actually another 2 that we can pull out of each of these. So I'm just going to kind of put a little triangle over it so we can distinguish which pieces we have going together. Now this one has a 2, but this one has no more 2, so we can't actually pull that third 2 out of each term. But both of these also have an x as a multiple, so we can actually factor an x out as well, because it's a multiple, even though it's not a constant. Okay? So when we factor out a common factor, we're still going to be left with the same number of terms that we started with. It's just we pulled multiples out of each of them. So altogether, we pulled a 2, a second 2, and an x all out of each of these two terms. And we can see the only things that are left over that I haven't grouped together here. We have an x left over in this first term plus this last 2 left over here. And we can look back at these two terms just in case. Is there any other multiples that we can pull out of each of these two? No. Right? And especially if you broke it down like this, it should be very obvious that we didn't miss anything. Now, this is a little unnecessary. I mean, we can actually kind of combine some of these terms. So we know that 2 times 2 is 4. So on the outside of the parentheses, we would actually have a 4x. And on the inside, we would have an x plus 2. And again, if we wanted to make sure that we factored it correctly, if we distribute this expression to the 2 terms on the inside, we better get what we started with. So 4x times x, well, this is like 1x if you wanted to think of it that way. So 4 times 1 is 4, and x times x is x squared. Because remember, the square, the exponent, means how many of those bases we have multiplied together. So since we're multiplying them, that wouldn't be 2x, that'd be x squared. 4 times 2 is 8, and there are no x's here. So one of them and no more of them would still leave us with 1x. So we can see that when we distributed, we got what we started. So we know that this expression will factor into 4x as a greatest common factor on the outside, and x plus 2 still left over on the inside. So for the time being, we'll consider all the multiples broken down, but as you get used to this process, you probably don't have to write them all out. You can kind of just recognize that maybe 4 and 8 have a common multiple of 4. 4 and 8 both are divisible by 4, so we can pull that out. So you can kind of skip some of the steps as you feel comfortable. But for the time being, writing them out definitely shows what can stay in and what can come out, so we don't miss anything. And then redistributing, always redistribute just to check. Build your confidence. Once you feel like you're getting them right and you're working through the process correctly each time, then maybe you don't have to check them quite as often. But it's a good practice for starters. All right, let's try this one. So this one looks a lot different than the first two that we've done, but we're still going to try to consider how many terms we have. So just like I did in the last one, I'm going to actually break down and kind of remove all the items here and just draw like a blank space to separate what pieces are actually being multiplied, so I can kind of justify which terms or how many terms there are. So 3 is being multiplied by x, which is being multiplied by this entire expression in the parentheses. So if we want to break this down, we can say that 3 is being multiplied by x, which is being multiplied by this entire group of parentheses here. Then we're adding 7 times this whole set of parentheses. So again, it's 7 times this other space here. So this should help distinguish that there's really just 2 terms. This whole piece is 1 term, plus this group of multiples is this other term. So from here, we can definitely see which pieces are being multiplied. Now, unlike the first two that we just did, where we considered constants as values that we can factor out, or variables like x, just x to factor out, this one actually has an entire expression that is a multiple. So if it's a common factor between the two, then we would need to make sure that these two expressions, since each of these terms has that expression, are exactly the same. So this first expression is a positive x plus a 4. This second expression, the second term, is also a positive x plus 4. So since these are exactly the same, we can do this the exact same way and say, okay, from both of these terms, right, and I'll just set it all up here, from both of the terms that we have, we can actually factor out the expression x plus 4. So I'm just going to kind of leave it in the parentheses because we're still being multiplied. So we're going to remove the expression x plus 4 as a multiple from both of these terms, as I have them still underlined. And then what's left in this parenthesis would be what's left over when this term is removed. So if we look at it, I mean, if we have the 3 and an x plus 4, and we take away this x plus 4 expression, we're left with just the 3 and the x from this first term. Plus, we have the 7 and the x plus 4, but if we took away the x plus 4, then we're still just left with the 7 here. Now, from these two terms that we have left over, just to make sure, if we look back at it and look to see if there's more multiples that we can pull in, both of them would need an x term, an x multiple, to pull an x out of each of these terms. So we can't factor an x out because this one doesn't have one. The only multiples of 3 is just 3 and 1. The only multiples of 7 are 7 and 1. So even the constants don't have a common multiple that we can factor out. Now, since this one was kind of set up as grouped kind of expressions, if we wanted to distribute it, we could. But to make it look like what we started with, we would need to consider that we're actually distributing this whole group back to each of these, which makes for a pretty easy check, because if you put this group to the 3x, then we have the 3x then being multiplied by the x plus 4, and then the 7 also being multiplied by the x plus 4. So we can kind of see that we get the same value out. Yeah, I know that's not normally how we would kind of distribute two terms in one group to two terms in another group. We would do more like a FOIL method. But just to try to make sure that we get back to what we started with, we can still see that it works out. So we know that this is going to factor down to, I'll just rewrite it without all the underlines and stuff. This is going to factor out to x plus 4 and 3x plus 7. Okay? All right, I want to try another one of these, because the grouped kind of expressions makes it a little hard to see maybe how things are going together. So we'll practice this one more time. So let's give this one a try. I'll kind of leave this one up here so we can kind of consider how we're starting off. Again, we want to justify how many terms we have, so we're trying to look for multiples. So again, if we look at, 6 times x squared times this entire parenthesis minus 9 times x times this entire parenthesis, we can kind of separate them out. We have the 6 times the x squared value times the parenthesis minus 9 times the x value times the parenthesis. So removing all the values and just looking at the operations that link them together, hopefully this helps kind of distinguish where the terms are. So again, we only have two terms. So if we're trying to look at the values, the multiples that we can pull out of each term, hopefully this will get us going, start us off good. Now what I would say is, this one, there's a lot more going on in this one, although it kind of looks a lot like this first one that we did. So I'm going to actually do this in two phases. Now, after you get a little better at it and you want to just do it all in one step, that's fine. Right? You can still kind of check your work as you go. But since I have this whole expression here, again, I want to just make sure that this expression is exactly the same in both of them, which it is. We have a positive 5x and a negative 1. We have a positive 5x and a negative 1. So again, I'm going to actually just pull this whole expression out of these two terms. So what I'm going to do is I'm just going to open up a set of parentheses, make sure I'm not losing things, because even if I factor out a greatest common factor, I should still have two terms left from what I pulled out. So again, I'm pulling out the 5x minus 1 as a multiple from both of these terms. And then we can consider what's left over. If I just kind of ignore the 5x minus 1, I can see the multiples that I have left. In this first term, I have a 6x squared, and in the second term, I just have a minus 9x. So even though we did factor, generally speaking, if they ask us to factor, we want to factor as much as we possibly can. So in most cases, this wouldn't be correct if you're being asked to factor because you're trying to go as far as physically possible. So after we factor out this expression, we can consider these two terms again and look to see if there's common multiples. So if you wanted to, you could break down 6 into multiples of 2 and 3. X squared is, again, x times x. We know that 9 is 3 times 3, and we only have 1x here. So for the time being, I'm just going to go ahead and keep doing this. If you recognize that 6 and 9 are divisible by 3, and both of them just have an x, then you can just kind of pull it out without writing this down. Otherwise, we can actually see which pieces are common in both of them and which ones we can actually remove. So again, I'm going to set up and make sure that I have both terms still available. I still have this 5x minus 1 that I pulled out here. I don't want him to go away, even though we factored it out already. And then I'm going to look and say, well, again, I have a 3 that I can factor out of both of them, and an x that I can factor out of both of them. But that's it. So I'm going to pull the 3. These are already being multiplied, so I don't really want to distribute them into here because we're trying to break them apart. So I'm just going to kind of pile them up, kind of like we had out here. We had the parentheses, we're going to pile them up on the outside. So I'm going to pull this 3 from each of them and this x from each of them, and I'm going to put them out here. And then we can see what's left in this first term. We got a 2 and an x left in this first term, minus, and we only have a 3 left in the second term. Now going back and checking, kind of like we were saying, if I wanted to go from here back to here just to check, we already pulled this guy out, so I would just want to make sure I distribute this 3x to both of these terms, just to make sure I get the pieces that I pulled out just in this thing. So we know that 3x times 2x, we can say 3 times 2 is 6, and x times x we know is x squared, right? And then 3 times negative 3 is negative 9, and we have 1x here and none, so altogether, if we multiply, we're combining the exponents here, we just have 1x. So we can kind of see that even if we just pulled these guys out, we still have what we started with here. And same thing here. If we put these back together, we can see. If we put these back together, we can see they're grouped, so it makes it a little easier just to check. So we know that this thing all together is going to factor into, we got the 3x. I'm just going to rewrite it a little cleaner. And then we have the 5x minus 1 as a multiple. And then lastly, we have the 2x minus 3. Right? And we couldn't factor any more out, so we know this is as much as we can factor out of these. Okay? So this has a lot to do with just the common factors, greatest common factor. Right? If we wanted to go down the list of our priorities, we could have worked with, okay, now that we factored out the greatest common factors, we would want to consider that there's 2 terms left over, and then maybe go down our list of priorities. But just focus on the greatest common factors for now, just so we got that